Hello, my dear students. Why I didn't say that started the record. Hello, my dear students. I hope everything is okay with sound. Let me to check, please. Is it? Yeah, it's okay. No idea why a system doesn't say record started. It's introduction into major because we yet have some classes, practical classes. You understand, at least half of you understand that I was busy with another discipline, and after I gave you all the possible tasks in introduction, I postponed a couple of last classes until I do not finish with another discipline. Look, we yet have a couple of classes in record to be, and 2 classes should be online. I ask the same questions that I asked it in another discipline when it's convenient to you. In order you understand, we have time difference approximately 6 or 7 hours. I may start working already from 7 o'clock by Kiev, certainly. That means that at your country, at your place, it's 13 or 14 at this moment. Or if it's more convenient for you at evening, let's meet at evening. No problem. Just think over this question if you watch this video, and the same question I'm going to ask you in TikTok chat. And what I mean to talk in this class and maybe even in next class yet about some engineering important matters that are called dimensions, tolerance, errors, accuracy, precision, and so on. In order we understand terminology without problems, I'm going to use some files with slides, and I'm going to use my own notes. As a rule, you've seen how I do it. And to show you a couple of movies also. But what should I say? I may recommend you as a literature also to use that book, Fundamentals. Where is it? I already opened it at proper place. Do pay attention. Chapter number 5. And in this chapter, they talking about the same dimensioning, tolerances, and so on. What I need you to understand when it comes about dimensioning and accuracy in engineering, what do we mean? We mean geometry, sizes, and their accuracy. They are corresponding to the sizes given in documentation. And we mean also such parameters, they are called surface finish. It's the group of parameters, actually. The group not even of parameters, but the group of parameters, groups of parameters, something like this. And we are going to talk about this and to have at least some slightest idea about. Okay, to start. Time I see. I hope I'm not over time this time. Well, and what is also interesting why we're talking about this, because we need to understand what is effect of surface finish, effect on surface finish and sizes of manufacturing processes. Actually, even afraid to start something with like I'm already a bit dispersed, too much information, too much sources of information to you, and do not understand what to start with, really. What you see right now, it's definition from standards. And those standards, maybe I should start with explanation even of 2 different approaches. I open it on purpose here. It's once again remind you, if I don't know, I think it's not available for you, but if it's available to you, I need to explain that this media, this Wikipedia, so-called free encyclopedia, it's not reliable source in terms that whoever, do forgive me, may write in this free encyclopedia. And yes, they have some team of redactors who watch these changings, but do forgive me, especially when it comes about some social practice, some events, some so on, it's not trustworthy completely. When it comes about engineering, mostly it's usable, at least in general matters, in mathematics, engineering, and so on. And why I use it right now to show you two chapters with different names. Pay attention: geometric dimensioning and tolerancing, and geometric product specification and verification. It's two different possible approaches to the same matter, which is called piece of, piece of trash. Empty space. Have found some empty space for us, which is called GPS. We understood it typically as global positioning system. It's not. Geometric product specification. System of standards about this geometric product specification, or as I said you, it's called GPS. It's different in different countries. Here we see this GPS and we. It's a European system, which is based on ISO standards, you see. And the one which is named G, D, and T, it's based on American standard. American standards of so-called American Society of Mechanical Engineers. I already mentioned it dozens of times. Maybe you already know it. And they have standard as to GPS, that one. It's the only standard. So it's normal approach of them. They have one standard book which may consist of whether it comes about GPS, whether it comes about welding or in other matters. It's always typically always one rather big book, no, 100 of pages, 200 of pages, with definitions, explanations, applications, tables if necessary, with data, and so on. European standards, typically it's system of standards, what pay attention, at least the same thing, object, one object, geometry of object. It's explained in three different standards, and they are standard not so big, and they are permanently intertwined with referring to each other, and so on. Some basic means, basic meaning, some basic definitions we will watch, and mostly these two system of standards, they are corresponding to each other. Mostly, they have, like it's given in one of articles, they have little nuances in differences, but mostly it's about the same. And I should have been opened one more picture, one more page to show you. Forgot to do it at all until I didn't start talk. What they understand as surface finish. Surface finishing, it's a product process, do forgive me. Surface finishing, as you might see there in search, it's a product processes which resulted in that or another surface finish, and surface finish is understood as some different sub parameters. Surface roughness, and it has the group of parameters described. Surface waviness, the same group of parameters described. In so-called lay. Lay, I'm not see. No, here is it given lay. Flat, ideal, так, doesn't matter. Lay. And patterns of this lay are, we already notice it. We are notice it. What did I say? We are notice it. It's out of English grammar at all. Don't pay attention. Let's come back to the story. Well, the first, maybe I will follow to my own notes. First, we need to understand sizes. Size, you see, it's maybe with some different adjectives. Nominal size, so-called general size, and nominal size, basic size, they are seems like they have the same meaning in their standards. No, practically the same, because nominal size in our country is understood like size given in documentation, and the same meaning they have in, you see, in basic size. Next, after object was produced, after it was implemented in the real life, it has so-called actual size. Actual size, measured size of the finished part after machining. No, okay, let it be like this. Or any object, it has actual size. If this object of artificial nature, it means it was manufactured, produced by people. People had some documentations, more probably, and in the documentation, it was given some nominal size. Next was realized, implemented into actual size. Quite clear that these objects, if they are produced in big amount, and even the only object that you are producing, actual size not compulsory coincide with the nominal size. Difference between nominal size and actual size, it's called with the name error. It doesn't mean that it's bad. It's not bad, not good. It's just such a terminology. Difference between manufactured size or actual size and size given in technical documentation is called error. Error might be to plus and to minus. How to understand? Is this error acceptable or not acceptable? So we're talking about quality already somehow. If something is acceptable, we will consider it qualitative object. We agree with this error, yes. And this acceptable, not acceptable in engineering, it's generally assessed, estimated with comparing to limits, and these limits has name tolerance. Tolerance described with upper limit and lower limit, and in early time in the drawing it was early times when some when in drawing something was given like diameter, for instance, 20 plus 5 minus там, let it be 3, it was understood as normal designation of tolerances. But for convenience and for talking about the accuracy without mentioning the dimension, no, for instance, look, accuracy. I didn't say what we understand as accuracy in general. No, I already said that in another classes and in both of disciplines. Accuracy, according to ISO standards about system of quality management. Oh, sorry, quality is quality we understand as degree of correspondence of object or service to the customer need. And accuracy is a sort of geometrical quality, actually. Accuracy is correspondence of object sizes to sizes given in drawing. But degree of correspondence, do forgive me. Accuracy is degree of correspondence of real object sizes, these actual sizes as it's given in American system, real objects to the sizes given in drawing. Degree of correspondence. What does it mean, degree of correspondence? Not look. What is tolerance here? I should give here 0.5, not 5. Great. It was too much not qualitative. No, let it be even 5 and 3, it doesn't matter. In just we have no such tolerances in real life, you understand. What is tolerance here? What is the field of tolerance? No, let's draw the line in order to recollect and in order to imagine with this. What here is 0.5, here is minus 0.5, and where this limit of permittable sizes? No, we understand that it's here is somewhere the size, and what are these limits where they are? Somewhere here and somewhere, not somewhere, but exactly there. we have some permitted limits of deviations. What it equal to altogether? 0.8. Without explanation where and how it's displaced with respect to the middle line, it's 0.8. So to this size, 20 and 0.8, it's some percentage of this size. Now let's write down another value with the same limits. Let it be diameter 200 now, and the same deviations. Upper deviation 0.5, lower deviation minus 0.3. Tolerance is the same 0.8. But what about accuracy? Let me to show you simple tricks that you maybe already have seen from me. Not sure. 0.8 with respect to the 20. 4%. Yes? 4%. No, I mean, if we multiply it on percent, it will be 4 on 100%. Accuracy in this case, 4%. Now, the same 0.8 with respect to the basic size or nominal size 200. I hope you see already what it comes about. It's less than half of percent. So which object is more accurate? Which object, both of objects have the same tolerance as a limit of sizes, but which one of them is more accurate? Where demands of accuracy more strict? Of course, in this object. So what I'm talking about, how it's appeared these ideas of international quality grade. In order to understand with this, whether it comes about accurate, not accurate, let's say, object, it's more convenient to talk about degree of accuracy, degree of tolerance. And maybe that was the reason that around 70 years ago, people has start talking about so-called tolerance grades. And these international tolerance grades next also were added, practically at the same time. They were added with additional designation. For instance, look, when we're talking about this size, diameter 20, plus 5 and minus 3. And now let's imagine that we have the same tolerance, 0.8 color. The same tolerance 0.8, but this tolerance is belong to diameter 20, 0 minus 0.8. Diameter 20 plus 0.8, 0. Next some piece of yesterday trash. Next, plus minus 0.4. Pay attention, quite the same tolerance, yes? It's 0.8 each time. But if we start placing these tolerances in different places, we will see that in one case it comes about objects of such permitted sizes. In other case, it comes about of those sizes, and so on. So demands are obviously different. Whether it's important or not, for single object, not much. But what if we're talking about interacting objects? If we're talking about so-called fits, that it will be important. And that is why values, figures that we understand as tolerance grade, they are usually accompanied with literals, and those literals, they show position of the tolerance field with respect to the axis, with respect to the nominal size, to this middle axis. Let's continue to see what we have. And is it written somewhere here? The fit? No, maybe not. And pay attention that this tolerance, it may be so-called unilateral and bilateral. It may be for the size from one side like I have shown. It's unilateral tolerance. I Seems like I didn't show another side. And it's maybe also given for both of sides. For instance, if I have tolerance uh, like this, and size is visible, and we understand it comes about the whole size, it means that this tolerance field is distributed to both of sides. Well, let's not talk about this right now. Let's talk about fits. And pay you attention. Fits may be, where is our picture? Yep. Now, here is the picture which explain us those matters about tolerances, no, in graphical way. Да? Tolerances, upper deviation, minimum upper, bottom deviation, or low deviation, and how they interact in different objects. Usually, we're talking about so-called shaft and hole. Now, pay attention that no, we understand. I hope you understand it without explanation that when it comes about shaft tolerance minus inter the body of the shaft, and when it comes about the hole part with hole tolerance minus inter the body of the hole, it means like it's inter empty space. Do forgive me, not in the body of the part, into the space of hole, and here we see that sizes may create so-called fits, their combinations, patterns of their coincidence or non-coincidence. And those fits, they may be of some types. If all the possible sizes of objects, they do not interact, they do not interfere, not intersect at all, it's so-called clearance fit. Because in any case, whatever object is, you have clearance. It's maybe so-called interference fits. Whatever object size, you always have some interference. Shaft is always a bit greater than the than the hole. There are so-called tight fit also, and another names for these fits are available for different systems or designations. We will see at least four different fits names in different designations. And there are so-called transition fits, which may be S with interference, S with clearance. Next, what I've been talking about, that it's also important to understand in terms of fit. It's important to understand where we have this tolerance field, because with the same tolerance field, it may appear quite different fit. With the same tolerance field Z in both of objects. And let's take a look once again onto source. Maybe not that source. Let me to see maybe this one. No, it's about mentioning. Just to show you, to illustrate you this idea. Talk about other attributes we're going to talk. And this picture explain the same terminology. Pay attention according to the American standard. Well, now you see so-called running fit. Another names of fits has appeared already, as you might see. And in American system, look, these fits are called generally running, sliding, and press fits, if I'm not mistaken. No, press fit maybe it's in English. Look, how many names of different fits depends on the pattern of an interacting, as I said. Loose fit, loose running fit, free running fit, close running feet, and so on. It's about clearances, clearance feet. In what here is it's explained more clearance and more interference. Да? It's in another terminology clearance feet. Sliding feet, locational clearance, locational transition, and they are in so-called transition fits in another terminology. And these one are already interference fits. So don't be confused with different names. Now certainly you will know that they just in English, I mean, that they just belong to different systems. In our country, we usually use three types of fits in name. Or maximum, we're talking about the very tight fit, let it be, some no indirect translation. But literally we have only three fit names using them, and in order to characterize the how much free fit or how much tight fit, we're just using the combinations of those literals which show the deviation from different surfaces. Let's come back to the explanation that you see here. Here is we see typical designation of objects with respect to this international system. First we have size, next we have designation of tolerance fit, tolerance grade, and position of tolerance grade with respect to the so-called fundamental deviation, with respect to the middle axis, with respect to this axis of this size. And pay attention that altogether it's called tolerance grade, and value it's called international tolerance grade. They are exactly related to their size of object. In order to understand which values are hidden under this designation, it's always necessary to open reference book. Or in modern software for drawing, for 3D modeling, those reference books, they are already inbuilt, let it be. And all the data, if you need to dimension something, all the data in the view of values by your click appear. If you appoint some tolerance grade, you may show it either as a tolerance grade or as values. What is more appropriate to show in a drawing, tolerance grade or values? Usually it's explained like if we no, what if you do something by hands, if you're employee or you need to measure something, is it your problem to run somewhere to library for the book, like reference book, and to watch what is the tolerance grade, do forgive me, values, instead of working? Of course not. So when you prepare the documentation for using in shop by your mechanics, by your workers, of course you have to give all designations in so-called simplified way. I mean, you show values like plus minus 0.3, for instance. If documentation is directed to another engineer, in this case, more appropriate to show international tolerance grade. And it's considered like, I don't know what about China, but all over the world and in our countries also, it's considered incorrect if you show both this and that. Because by mistake you may, no, actually, occasionally you may do mistakes either in one or in another designation. And finally, it will be contradictory information in the grade, in a drawing. So typically it's shown either or. Either tolerance grade is shown by litera and number of international tolerance grade, or it's shown the values directly, which more convenient, as I said, do in a shop. Так, about these ISO standards. Pay attention. If I scroll back, we will see very similar matters. Nominal size, basic size, actual limit of size, and so on. It was American story. Here it's European story. Basic size, deviation, upper deviation, low deviation, fundamental deviation for both parts. It's for the bilateral doesn't matter, bilateral tolerance. Well, and tolerance the difference between maximum and minimum size limits on a part. Да? Deviation, I hope you understand, it's the portion of error, actually. Upper deviation, lower deviation. No, it's also maybe referred to the tolerance field, like upper deviation and lower deviation. Here is practically explained what I already said, that combination of IT grade and this fundamental deviation, it's considered like tolerance grade. Well, that we have seen already. And now we see the whole pictures of different systems. These fits, they as appeared, they are given in different systems. One of them is called a system of hole, another is called system of shaft. Hole basis. In the system of fits, where the minimum hole size is the basic size. So we're relying on the hole size. And usually it starts with the what I didn't reminded you that deviation in fit, deviation of hole. How to understand which part is where? No, if you have the size in junction, you have size 90 and international tolerance grade, for instance, or 60 tolerance grade, like it was here. No, да? 60, ой, what? 60 tolerance grade. How to understand which one? Big literal belong to the part with the hole. Little literal belong to the part with the shaft. Shaft, it means anything that is so-called male part. No? It may be pin, it may be shaft, it may be whatever protruding elements which is inserted in the hole. Wait, sorry, what I did. I'm afraid I did something completely wrong. I jumped out from the story. Да. Mostly, you see, those systems, they are similar, but pay attention. When we see them together, seems like they are very similar, yes? But do pay attention, where the basic line, red line, you see, this one, and here, red line, pattern looks very similar, but a red line, either it's belong to the surface, and you see that all the surface to the hole, and you see that all the holes are given here with fundamental deviation h, which started from 0, and to the depth of the part, goes to the depth of the part. And when it comes about the system of shaft, pay attention. Shaft is given in deviation, fundamental deviation h always, and it's go inside of the part next this limits to the shaft size. And hole may deviate to the different places, to the different position with respect to the shaft nominal surface, let it be. So which one is more appropriate, which one is more convenient? More common to use system of hole in dimensioning. It's more convenient. In some exclusive cases, we use system of shaft, but mostly all the engineering tolerances, they are based in the system of hole. Do forgive me. Well, again, it's about different names of fits. You see, here is again American names on one side, and our symbols that used actually all over the world. This international tolerance grade, despite the fact that it was started somewhere in Europe, seems like now it's accepted all over the world. And as I already said you hundreds of times, that engineer may talk to each other by pictures, without any language. We may understand each other because we have our own engineering language, international language of drawings, of pictures. Right now, we see the tolerances grades, which fixed, like belong to different processes. I should say that some of these processes, they are even overestimated here. For instance, what that one, drilling. No, certainly it's should be a little bit far. It's not 10, 11 accuracy grade. It's already tolerance grade. It's already like overesteemed. Typically, drilling is rather rough process. And by such diagrams, we may understand their, let's say, limits, available limits of that or another technological process, of that or another technology. That if it comes about the accurate hole, even cylindrical hole manufacturing, what like this, for instance, 7 tolerance grade, you see it's not reachable by drilling. It's even more non-reachable by drilling that it's shown here. Boring, in some terminology, boring is understood as turning the hole. In some terminology, in some literature, it's maybe considered like countersinking also. It's processing of hole with a bigger amount of blades. With the tool that, no, in contrary to the drill, it has more blades, and due to this, it's more accurate. And here is you see reaming. Reaming, it's already may work even 6 accuracy grade. Tolerance grade. I permanently do the same mistake in explanation. No, it's just should be preserved terminology. That is why I should say tolerance grade, tolerance grade. If I pronounce accuracy grade, no, do forgive me, I mean tolerance grade. What I already said about the different systems designation, you see, the same. If you see somewhere there picture like this, more probably it comes about fits, yes. And to understand whether it comes about the, oi, get lost. No, do forgive me. Here is, you see designations that certainly differ from what you already have seen. Yes, like 1 liter and tolerance grade. It's for fits, and in these designations like RC, LC, it's mentioning of the name of fit. It's American system. Moreover, in our country, literally 30 years ago, it was, no, more than 30 years ago already. It was in the middle of 18th accepted this system of designations. In our country, we also had, in our countries, we had different system, and it was so-called class of accuracy. Somehow it was similar to this story, and these classes of accuracy, they also include, besides of tolerance class, tolerance grade, they include the surface finish grade. But it's not quite convenient, because not always the tolerance grade for geometrical size exactly correspond to the tolerance grade to surface finish. Demands to surface finish maybe not so high, like demands to the accuracy of size. Or in contrary, demands to surface finish may be very high, higher than demands to tolerance of sizes. And in this case, it's more convenient to talk about different systems separately, about sizes, separately about surface finish. No, different names of these clearances. I hope it's more than enough. And do try to talk now about the so-called dimensioning. I didn't say any word about another things that I promised you to explain, or to remind you not to explain. Look, once again, we have so-called accuracy, and accuracy is understood as degree of correspondence of geometry to sizes to geometry given, degree of correspondence of real geometry to sizes given in a drawing. So actual sizes, degree of correspondence of actual sizes to the nominal sizes. And we understand that accuracy is so-called relative characteristic whatsoever. Exact characteristic only in figures, only in values. And in values it's given in the view once again of upper limit, lower limit, or it may be called upper deviation, lower deviation, depending on which literature you use. Altogether, this upper and lower deviation, they create so-called tolerance field or tolerance. And tolerance we understand as limit given to the so-called real sizes. In order to characterize tolerance, people have agreed to talk about not just absolute values for convenience of engineers, but to talk about so-called accuracy grades. And these accuracy grades actually they are percentage to the size. And in our reference books, the exact values of tolerances of upper and limit deviations, they are given with respect to size of object, like this, like that, or whatsoever. And it will be given the line of columns where you have accuracy grade. Вернее, more exact to say, it will be international tolerance grade without litera, international tolerance grade, and it will be given the field of tolerance depending on the site. And if necessary, it will be also given in exact way, so-called tolerance grade, with considering the fundamental deviation where the field is placed with respect to the axis. Well, let's start talking about dimensioning in a drawing. Once again, didn't say what is preciseness. And even I prepared for you a couple of videos to show that in my own storage, let it be. Let's call it like this. And what this video is about. Usually, in order to explain difference between accuracy and precision, no, now it's understood, not just understood or accepted by society of engineer whatsoever, community of engineer. It's given even in standard what we understand as accuracy and what we understand as precision. In early time, precision was understood as the most high accuracy, like accuracy grade of high level. Now, what is understood as precision? Let's say that accuracy is degree of correspondence of geometry to the demanded geometry, degree of correspondence of real geometry to demanded geometry. And precision, it's maybe said that it's understood as repeatability of errors, repeatability of deviations. Also, this term precision, it's applied either to manufactured objects or it may be applied to the results of experiments. Typically, how it's explained, and practically the same explanation we will see in that movie. How precision is explained. On example of sorry, there are tracks of another disciplines. We studied all very interesting things in that another discipline. And I think it was interesting. I hope it was interesting. Let's draw something that you certainly recognize. It's so-called target for shooting. And we will shoot right now. Middle, middle, and let's do shooting. Or for instance, we did some things like this, like that, like this. Is it Accurate or precise? If we assess this one, we are talking about, look, what is accuracy? Accuracy is degree of correspondence. Accuracy is how far it's from the center of the aim, target, sorry. Here is not accurate. Here it's more accurate. That is the most accurate at all. Yes, that is also rather accurate. Whether these results are precise or not? No, they are not precise. They are too different in these quadrants, for instance. Look at these results now. Z1, Z1, Z1. They are accurate. No, if we are talking about, let's remove this one. Red one will be somewhere here, and this blue one, they are rather far from the center. They are accurate or not? Red one are accurate with respect to the blue one, and blue one are precise. Oi, like this. That is accurate versus precise. Precise. Accurate its degree of correspondence to the size given in documentation, and precise its correspondence degree of correspondence between some real sizes without referring already to the so-called nominal sizes. You see? Now, if we're talking about accuracy of manufactured objects, so as I said, accuracy, its degree of correspondence to documentation, to demands, let's say, and preciseness is the degree of correspondence to each other. It's the repeatability of object sizes, approximately like this. And this preciseness in aircraft manufacturing is appeared more preferable time to time, even than accuracy. However weird this idea sound, but in case of assembling, preciseness of sizes is more important than accuracy of sizes. No, that is idea of coordination and all these matters about coordination, not right now, but I hope you will remember this story that accuracy and preciseness, it's not the same. Now let's open, as I said, the short movie to watch. Where is it? No, when it what here is also explanation. You see, typically all the explanators, all the lecturers, they use the same visual examples. It's easy to imagine in such a way. Look, what does it mean? Accurate. They are rather close to the center. Yes. What does it mean? Precise. Wherever they are, they close to each other. Here is precise but not accurate because they are much far from the center. And these results are both accurate and precise. And I have two of them. One of them is completely boring, another not so boring. Which one? That one is less boring.
As the story goes, the legendary marksman William Tell was forced into a cruel challenge by a corrupt lord. William's son was to be executed unless William could shoot an apple off his head. William succeeded, but let's imagine two variations on the tale. In the first variation, the lord hires a bandit to steal William's trusty crossbow, so he is forced to borrow an inferior one from a peasant. However, the borrowed crossbow isn't adjusted perfectly, and William finds that his practice shots cluster in a tight spread beneath the bullseye. Fortunately, he has time to correct for it before it's too late. Variation 2. William begins to doubt his skills in the long hours before the challenge. and his hand develops a tremor. His practice shots still cluster around the apple, but in a random pattern. Occasionally, he hits the apple, but with the wobble, there is no guarantee of a bullseye. He must settle his nervous hand and restore the certainty in his aim to save his son. At the heart of these variations are two terms often used interchangeably: accuracy and precision. The distinction between the two is actually critical for many scientific endeavors. Accuracy involves how close you come to the correct result. Your accuracy improves with tools that are calibrated correctly and that you're well trained on. Precision, on the other hand, is how consistently you can get that result using the same method. Your precision improves with more finely incremented tools that require less estimation. The story of the stolen crossbow was one of precision without accuracy. William got the same wrong result each time he fired. The variation with the shaky hand was one of accuracy without precision. William's bolts clustered around the correct result, but without certainty of a bullseye for any given shot. You can probably get away with low accuracy or low precision in everyday tasks, but engineers and researchers often require accuracy on microscopic levels with a high certainty of being right every time. Factories and labs increase precision through better equipment and more detailed procedures. These improvements can be expensive, so managers must decide what the acceptable uncertainty for each project is. However, investments in precision can take us beyond what was previously possible, even as far as Mars. It may surprise you that NASA does not know exactly where their probes are going to touch down on another planet. Predicting where they will land requires extensive calculations, fed by measurements that don't always have a precise answer. How does the Martian atmosphere's density change at different elevations? What angle will the probe hit the atmosphere at? What will be the speed of the probe upon entry? Computer simulators run thousands of different landing scenarios, mixing and matching values for all of the variables. Weighing all the possibilities, the computer spits out the potential area of impact in the form of a landing ellipse. In 1976, the landing ellipse for the Mars Viking lander was 62 by 174 miles, nearly the area of New Jersey. With such a limitation, NASA had to ignore many interesting but risky landing areas. Since then, new information about the Martian atmosphere, improved spacecraft technology, and more powerful computer simulations have drastically reduced uncertainty. In 2012, the landing ellipse for the Curiosity lander was only 4 miles wide by 12 miles long, an area more than 200 times smaller than Viking's. This allowed NASA to target a specific spot in Gale Crater, a previously unlandable area of high scientific interest. While we ultimately strive for accuracy, precision reflects our certainty of reliably achieving it. With these two principles in mind, we can shoot for the stars and be confident of hitting them every time.
Long, sorry. Certainly we will not use second one. If it will be necessary, I'll send it to you. Well, the main thing you already understand. Both it's important, accuracy and precision, but there are two different concepts, different ideas. And to understand precision as the highest level of accuracy, it's not. Precision is not compulsory accurate. Accurate is not compulsory precision. You understand it. Of course, it's great when we have both accuracy and precision, but time to time, as I said, we are sacrificing the accuracy in aircraft manufacturing to the precision in order. What is great also in that story that precision, actually precision things what in this precision errors, precise but errors with low accuracy, they may be rather easy corrected. It's some systematic error here, some problem of equipment, for instance. which resulted in shifting of results, shifting of sizes, for instance, to some area. And it's more simple to identify what is the reason and no, to affect onto the reason. And next, your results may be just shifted somewhere closer to the center, да? Due to you affecting to the reason of this mistake, of these appearing errors. In case we are working with so-called occasional errors, which are wherever, not precise, in this case, it's more difficult to change technological process to affect onto that or another parameter of either process or equipment in order to get more close results. So precision is important, especially in aerospace application. It was very interesting example. So I waited up to the end of this animation about NASA satellite. You understood? Well, let's come back to what did I said here. What is interesting for us when we're talking about drawings, designations in drawings? Designations in drawings may be of different types. One of them are dimensions. You see that definitions may be different a little bit about dimensions. When we're talking about the object, we say usually that size object has sizes, and designation of these sizes in picture, in drawing, in the model, in a drawing, those designations, we call them dimensions. It's English terminology. In order we remember when we're talking about what we mean when we say sizes, what we mean when we say dimensions. Tolerance we have already understood, and surface. Surface, let's jump here. Here is surface. It's understood as exterior boundary of object. I have opened it somewhere here as a standard, but maybe already do not find it. No. Here is, yes, this British standard. It's to show you it's British standard. I already said you that European countries, they used to reissue ISO standard with the same number, but with addition. For instance, BS, it's a Great Britain standard, but it's completely identical to ISO standard with this number. And Germany, it will be with another designation, addition, like DN, if I'm not mistaken. And here is not about exact sizes or about tolerances or about something like this. It's about of ages. Ages are also important elements, features of the object. And each standard ISO, it starts with some terminology. And here is no terminology of surface. No, maybe I just forgot what standard I need to refer in order to see the same definition. That is definition from European standard. Surface is understood as exterior boundary of object with its surrounding. And let's come. It was here also. We've been here. Да. And here it's not definition of surface, as you might see, it's importancy of surface. That surface may affect to product performance. Surface may determine aesthetic of object, and also surface how actually surface affect product performances by that or another tendency in wear above the all, and it's not only. But that is one of important results, especially when we're talking about couple of objects, about friction couples, so-called. Next. About this we have already talked about so-called geometrical attributes. Those geometrical attributes, they are already related to another group of parameters, and despite of accuracy of sizes, whether linear or angular, we have also accuracy of shapes. Here is about accuracy of shapes already. Let me to show you designations, maybe you will recognize them. If you ever worked with engineering drawings, you already seen such things. Signs which refer to accuracy of shapes. And it comes about tolerance deviation. Just let me to show you the exact name, not here, in European standard. Forms, shapes, location, and orientation of surface tolerance. Not here. Вот они, на the group of standards, form, orientation, location, and runout specifications. No, do forgive me. It's it's in different system, this global product, global geometrical product specification in different systems, this G, T, and D, geometrical tolerance and dimensioning, and GT and V, geometrical tolerance, dimensioning, and verification. A little bit different names, but idea is the same after hidden after these different names, that we are interested not only in the particular sizes, but in the whole forms, shapes. And these shapes, they are given here. Look, if we compare two tables, we see practically identical sizes. And whatever system is accepted in your country, I trust you use that or another, and they, even your very own, it will be rather similar. And when it comes about the tolerances of shapes, forms, and runouts, we have such names: angularity, circularity, concentricity. Don't know whether it's worthy to show you exactly what that or another word mean, that or another terminology, especially if I'm going to send you those slides, for instance. But maybe you already studied this, maybe you already know it. In particular, cylindricity, it's deviation of cylindrical shape, deviation from cylindrical shape. You may understand that this may be some ovalness or not waveness over a cylinder, for instance, or something like this. The same with flatness. It's not compulsory explain it only with waveness of surface, this flatness. Parallelism, the same. How much differ two surfaces from parallel surface they should be, and so on. And what we're more interested in, surface terminology. Here is surface terminology. You see what it refers to. We have so-called top layer surface texture. We have altered layer and base material or substrate, as it's called. Mostly what we concerned about in parameters of surface finish, so-called parameters, we are talking about surface texture. Altered layer, it's layer which is a bit spoiled due to manufacturing process. I hope you do remember that we've been mentioned it hundreds of times maybe already by now. No, at least in second discipline, certainly. That after that or another process, object may be, for instance, heated up significantly and higher than temperature of so-called collective restructurization of material, and due to this, it's appeared another sizes of grains here. For instance, or in contrary, we may use some special heat treatment that we purposefully changing here the top layer structure in order to create hardened surface with comparatively soft inner portion, and so on. So surface texture next, it's explained already, defined with also some parameters. On one hand, it comes about the micro parameters. It's about surface roughness. Next, until I place here the picture, Surface roughness. Next, let's say pattern of direction of the surface roughness on the on the outer surface. Describe it with the word lay. Look here, it's written even predominant pattern of surface texture. How it's directed. Those pictures I have already even shown you in order to you to recollect. What, for instance, mill pass in this direction or in that direction, or it was circular motion of the mill where we have been come back. And waveness, it's already something like micro deviation of surface that may be registered by on long lengths, let's say. Here is its explanation about different parameters of the surface texture, as it's written here, or surface finish, as usually it's also called. Pay attention that this waveness macro deviation, it may be accompanied with some micro deviations on the way, and they are referred as roughness. And this roughness, it's no, we may imagine it like a long placed on some not linear line actually, and possible variants of lace, what we have seen partially, it's also here explained. Lace, it's how roughness is directed with respect to the main axis, let it be, of our object. In some cases, we interested exactly in lay direction. For instance, in some processing, like honing, for instance, manufacturing processes, we create lay of spiral way or something like this. It will be the lay of such a type. In the view of two system of helic lines, of spiral lines directed to different sides, in order to have surface scratched with such a pattern, what for? This honing of surfaces, it's created on purpose in order these surfaces has scratches which fill it with lubricants. It's for increasing the ability of object to save lubricants, something like bearing inside will be with hydrodynamic friction. And that one is purposefully done. So surface lay, it's something we're interested in or not interested in, depending on the object specification, depending on our needs. But it's important characteristic how this roughness is directed in the on the surface. About the surface roughness, surface finish, subjective term related, as I said already, to surface roughness, to the waveness and lay. How surface roughness is described? Usually it's described, let me to show you the picture. Usually it's described in two ways. There are two main parameters that we all know, so-called RZ, it's in absolute values. It comes about peak and values, so-called top positions are peaks, bottom positions are values. They may be different, you see, and the highest values in micrometers, RZ20, for instance, it comes about maximum peaks on the surface in the limit 20 micrometers. No, meter 10 minus 6. You understood. And there is another parameter. Another parameter is so-called RA. It has no clean geometric example. RA is something like average out of area, both under the line and over the line. It's not absolute value like AZ. But nevertheless, RA now considered like preferable. This parameter RA typically is shown in drawings without even letters. If you see a specific sign of roughness like this, without literals, just values, it means that it comes about parameter this roughness average. Well, and what is said here, that arithmetic average, you see, this parameter is called. Да? Very well. Arithmetic average. Так, and another parameters of surface roughness, they include also some specific things like steps. They have actually the two groups of parameters. Some group of heights, different heights of parameters, and a group of steps parameters. We not going to talk about this now. Maybe it will be too much for you. Or maybe you already studied this by the word. And what I'm interested in to show you the effect of different manufacturing processes onto parameters of surface. Here is, in contrary to the picture that we have seen there in Telegram. Yes, in Telegram, but where? Let me to jump again. Sorry, scrolling this. Oh, да, that one. Maybe I took it in here. Am I right? Oh, almost. Sorry. Yes. Here you see also different processes. You recognize their names. And with respect to parameter RA in English. But also it's given in some absolute values. What these absolute values? Look, here is parameter RA and absolute values. If it's in micrometers, it means that it comes about the RZ already. I hope you understand it. And no, the way I took these pictures I already do not remember, because it was not 5 years ago, but something close to 5 years ago, maybe somewhere internet. This one show us the different operations in tolerance grades, as you might see, and in this source you have explanation, not this one, that one. Да? We have explanation in absolute values. What is in absolute values may be achieved by that or another operation. And if you compare, for instance, the accuracy of, let it be abrasive process, да? Abrasive processes, accuracy, typical, plus minus, and 3 values after 8 micrometers, you see. And milling, let's compare blade, so-called conventional milling, conventional processing, blade type, or it's called multi-point processing. You see, it's 10 times worse. Drilling actually might be even more worse. Not like here it's written. What is also to be compared, cast iron and die casting. No, in their case, they didn't show here forging, for instance. They show only casting and metal forming only where its surfaces. No, it's interesting to watch all the parameters like it was here. Not all the parameters, but all the processes, and to compare the accuracy. And of course, it's not quite also possible to say about that or another accuracy of process, because some processes, they are characterized with very wide interval of this accuracy. For instance, when we're talking about the forging or sheet metal stamping. They may be in cold state, they may be in hot state. Hot state, it's low accuracy, it will be somewhere here in tolerance grades. When it comes about cold, it will be closer to this side, and so on. So it's not ideal way to represent the ability of that or another technological processes, but because to the fact that they are too different under the same name, it's hidden the whole group of different processes and fulfill it in different conditions. But in general idea, I hope you already understood. And what I was interested you to remind what we understand under the different terms, under the different words. So we have so-called absolute values, and those absolute values, they are different. No, the size, I hope you understand. Size is some characteristic of object, of real object. Showing of this size in the drawing, some designations, we usually called with the word dimensions. Dimension may be an angular, dimension may be linear. Next, we have so-called deviation of dimensions. Deviation of dimensions, they are realized in real objects. And in these terms, either we call it real size or actual size. It comes about real object sizes. These real objects, they are not so ideally coincide with some size given in the drawing. Size given in the drawing by values like diameter 20. It's so-called nominal size. It's disappeared. Here is, да? Nominal size. So real objects, they do not coincide ideally to this actual real objects with their actual sizes do not ideally coincide to this nominal size. Do forgive me. And the degree of correspondence to this nominal size that we understand as accuracy, it may be explained by different way. Actually, this deviation of actual size, of real size with respect to the nominal, we call with the word error. Manufacturing error, calculatable error, predictable error, and so on. Manufacturing error, it's something that already was realized into life. After you produce the object, you may see what this manufacturing error is. And in order to work with engineering objects, we need to set some limits. Those limits, they are called tolerances. And in order also to understand the accurate these tolerances or not with respect to the size of object, we implemented these international tolerance grades. Tolerance which is referred to their nominal size, like this approximately. And they are also accompanied with the so-called fundamental deviation. So we have tolerance grade designated with litera and number of international tolerance grade that show us where the limits really located with respect to the so-called axis, central axis, with respect to the nominal size. And one more important term that I hope you will remember is preciseness or precision. That is not, does not mean accurate. It means repeatable. No, literally, if we're talking about the accuracy rate, it's how close it's to demands, how close to the middle of this target. And precision is how close results of weather manufacturing or some laboratory experiment or shooting like it was in this animation, how close these results to each other. And what is preferable, accuracy or precision? If we're talking about the manufacturing of airplanes, we understand that we deal with assembly work mostly. 3/4 of time it's assembly work. And our final aim is to provide outer surface of airplane, but to provide this outer surface of airplane and its strength and its weight and so on, we need to assemble objects. Objects should be similar in sizes and assemblable. And in terms of assemblability, it's more interesting to have precise objects, more close one to another in sizes and shapes. If they are not ideally accurate, it's somehow compensated during assembling. Will not explain right now how, because it's very long run, very long story. But we have means of compensating of errors during assembling due to design elements, due to special assembly methods, and so on, in order to provide only the accuracy of outer contours, actually, seems like. It's not completely the absolute true, what I'm trying to explain right now. It's like simplification of our real true, real life. But for providing of assemblability, precision is extremely important. And this precision is one of the matters that we are working in the methods of coordination. In the general mechanical engineering, what is more important, accuracy or precision? Now, of course, you understood already, like it was given in some explanations, that both precision and accuracy are important. And why we have to choose between them? because they are provided by different approaches. Time to time, they are like you need to go on two ways simultaneously in order to provide both precision and accuracy. And either you're paying twice, and in this case, you have both precise and accurate objects, or no, considering what is more important for you in that or another application, you may select what is more important, precision or accuracy. Maybe it's too difficult and to understand yet, but I hope you understand it much later, maybe in some years when you start working. What is also necessary to remember about the sizes, about the accuracy, about the all other things, that in engineering, the objects characterized not only with accuracy of sizes, but with complex of parameters which are describing the surface. And surface parameters, they are no less important for us in many ways. No, first, surface as general, we are not even yet goes down, let's say, to the surface like this, no? To the to the surface of surface. In general, surface, it's important in terms that shape of object, surface of object, may be deviated in different ways, and these different ways, they are called these deviations of different in different ways, they are called roundness, angleness, parallelism, and so on. And they are designated in drawings with special signs, and also these signs are accompanied compulsory with values. Let me to show the book. It's about measuring tools of different types. Measurement of surface. No. Do not remember where I have it in the picture. Do forgive me. Maybe here. I have prepared it, but practically have not used it. Somewhere here it has this explanation about shapes. Да. No, you see this geometric dimensions and tolerancing. We understand that it's refer already to standard, to American standards. But here is pictures. Pictures. What we understand on that or another deviation of surface. And these micro deviations of surface may be with the name, as you might see. It may comes about a deviation of outer surface or of axis that I didn't say, sorry. And we see that they may be different. No, it's not shown here how it will looks like this wrong surface, but it's shown, we may imagine, what it comes about. The circularity, it's how close to the circle object is, either to the inner circle, to the outer circle. Here is deviation of this inner and outer circle given in a drawing, yes. Next, for flatness, for cylindricity, and so on. I hope you already studied this. I hope you intuitively may imagine this. Well, and this, let's stop on this. These micro deviations, they next, like we are going closer to the surface, these micro deviations next additionally described with group of parameters which are referred as surface finish. And surface finish in turn, it's include surface roughness, surface waviness, and surface lay. Surface lay you see right now, it's predominant direction, let it be, predominant pattern, as they call it, of how roughness is oriented on the surface. Waviness, it's micro deviation. Picture? No picture. If you have no picture, we don't need you. And surface roughness in terms, also waviness, it's characterized with at least two parameters, the step of waviness and the absolute height of waviness, to the top, to the bottom. And surface roughness. Surface roughness is described with the whole group of parameters. Some of them are absolute, some of them are, as you might see, calculatable. And the most usable, this one, which is called average roughness. No, arithmetic average roughness, okay. But also it's maybe measured in absolute values. In absolute values, its parameter RZ. Where is it? Okay, doesn't matter. And these absolute values, they are measured from the so-called middle line. What is middle line? No, it's some line that describe your, like this, they describe your size, actually. No, I hope that was already completely boring for you. Oh, I hope. I'm afraid. I'm not hope. I'm afraid. It was very difficult and boring subject for in my explanation. Do forgive me. And what I need you to remember, like basic terms, basic ideas. The difference between size and tolerance, I hope you already understood completely. Next, error, accuracy, precision, and tolerance. And I need you to distinguish this terminology clearly, what it comes about. No, maybe it's too late already to talk about this after we finish the whole discipline where we use this terminology. No, at least I hope after this you will remember about demands of accuracy to different objects in manufacturing, and you will have clean ideas as to the designations of these demands, let it be, whether it comes about providing of assembly assemblability of objects, or it comes about the providing of accuracy. And once again, remind you that in aircraft manufacturing, we are more interested, we are more interested in assemblability of objects than in their absolute sizes of like of separate components of parts. during manufacturing. So in manufacturing, our objects may be produced with some not purposeful deviations, but with allowances, with extra pieces of material on different sides, on different contours, for instance. They may be finished, non-finished. They may be purposefully not finished, even in terms of deformation. And next, especially when it comes about thin skins, for instance. And these deformations of such thin skins, finally, it will be fulfilled already in assembly jig without preliminary manufacturing process. And assemblability is so important in aircraft manufacturing. Why? Because, as I already said you dozens of times, that we mostly involved in assembly process during creating of the aircraft. However much parts we have in aircraft manufacturing, all the labor input of manufacturing, it's 1/3 maximum of our work. And next 3/4 of our labor input, and practically it means that 3/4 of time either we involved in the assembling. No, and what I said that practically 3/4 of time, it's not ideally the truth. Why? Because it depends on how many people you may involve in the assembling. And you do remember that labor input, its characteristics which more correct in description of all technological processes, all manufacturing processes, because labor input may be the same, and if you use more people doing the same work, they are processing simultaneously, let's say, they are fulfilling, covering the same labor input. More people, less time, but labor input more probably will be the same. So 3/4 of labor input were involved in the assembly work. If necessary, you involve more people, and in this case, time of assembly is shortened, but the general scope in labor input it's yet huge. Sorry, maybe it's rather boring class. Do forgive me. Next, maybe will be even worse in terms of whether it's exciting or not, interesting or not, because next I'm going to talk about coordination.